everyone, welcome to IMS Gate Academy. I hope you are enjoying our smart revision sessions. So in today's session we are going to discuss theory of machine, right? Already first session we have discussed about simple mechanism, right? Gate train we have discussed, flywheel we have discussed. In this particular session we will be discussing about the most important topic of theory of machine, that is vibration part, balancing we'll discuss, and finally the gyroscope also. Right, so this revision session will help you in the last revision time, okay, because in the last we have to focus primarily on the revision and solving PYQ. Already PYQs has been revised so many times, but now in the last touch that we want to give before the gate examination, right, is what? The revision of the important concepts, revision of important relations and the formulas, right? Audio clear? Thank you so much if audio is clear. Now we'll be starting the session. The first thing, everyone, there is a Telegram group for you people. You can join this Telegram group to get the PDF of all the live sessions that we are taking on the YouTube. Apart from that, you will get all the latest notification of the job. And one more thing, you will get all the quizzes which will help you for your competitive examinations like GATE and PSUs, right? So you can better join this Telegram group. The link is also given in the description. Okay, this is the link and you can directly go to the Telegram also by clicking on the description. Okay, there is a link provided in the description. And next, okay, so we have already launched our online live program in which we are providing more than 800 hours of live sessions. Apart from that, you will be getting theory books, exercise book and previous year question bank. And most important feature of this live program is the 12 mentorship sessions. These mentorship sessions are basically designed to help the students. You will be getting complete hand holding here, okay? And apart from that, in your preparation journey, you will not be alone. All the faculty team will be always with you. Wherever you are getting challenge, your faculty members will help you out in your preparation journey, right? Before the gate examination also and after the gate examination also, right? And after that, this is one of the most important feature, like test series you will be getting, okay? And one more thing, doubt solving portal, which is 24/7 available. Whenever you face any challenge in the numerical, please click the photo of that particular question, post in the doubt solving portal, and you will get the solution within 24 hours, right? So now we will start our session here. The first topic that we are going to discuss here is balancing, okay? And then gyroscope and vibration we are going to discuss. Now, in balancing, the first thing that we need to discuss here is the balancing of rotating masses, okay? Now, in balancing of rotating masses, there are two cases, static balancing okay, static balancing, and there is second case, dynamic balancing, okay? Dynamic balancing. Now, what is the basic difference between static balancing and the dynamic balancing? Please understand. In static balancing, all the masses are in the same plane. Are in same plane. Are in same plane. Okay, all the masses will be in same plane, but in case of dynamic balancing, masses will be in different plane. Will be in different plane, right? So that is a basic difference. Now, what actually happens if it is all masses are in same plane and if it is are in different plane, the masses? The difference will be what? In case of it is in same plane, you will never see what? The moment here. Only summation of forces, force equilibrium we will be doing, but in this case of different planes, we will be doing the moment balance, right? Apart from force balance, we will be doing the moment balancing. Now, please understand here. So, first of all, I will show you the diagram here, okay? Then you can easily understand. Let me show you the diagram here, first of all. right? Now let's suppose we have a shaft here. There is a shaft. Okay, so from the side we are observing, and different masses has been attached to it. Different masses has been attached. Let's suppose like this. Like this, different masses has been attached. So you can consider this as M1, this one as M2, M3, M4, like this. So different masses has been attached. A very important point here, guys. All the masses are in same plane. So when all the masses are in same plane, we can easily say that the force equilibrium only we have to do. Okay, there will not be any moment. So only the force equilibrium we have to do it here. Okay, so what are the equations that we need to apply here? Summation of the forces along horizontal direction and summation of the forces along vertical direction. These are the two equations that we need to follow here, as all the masses are in same plane. So basically this observation you will have when you will observe it from one of the side. Okay, one of the side you will observe. So shaft will be seen as a point, single point, if you observe the shaft from one of the side. If I observe from the front, entire length of the shaft will be visible. Okay, so it depends from where you are observing the given shaft. Now coming to the dynamic case where the masses are in different planes. So let us see this part. Okay, but in this case I will draw the front view. In this case I will draw the front view of the shaft. So what happens here in this case? So masses will be attached in different planes like this. Like this it will be there. So you can say this is M1, M2, and this is what? M3. Final last mass is M3. Now as this are in different planes, what will happen? Forces are in different planes. So this force can have a moment here, this force can have a moment here. So there will be what? A moment thing, and we need to ensure for proper complete balancing, moment also should be 0. Because if there is a moment, there will be a tendency of rotation. See, always remember, when we say any system to be in equilibrium, when both translatory effect and rotation effects are under equilibrium. Summation of forces should also be 0 and the summation of moment should also be 0. Both the things we need to take care here. Okay. So in this case, the equation that we are going to use, okay, will be summation of forces along horizontal direction 0, summation of forces in vertical direction 0, and summation of moment in vertical summation of moment basically should be 0. Now about which point? At all the points. Don't always like confuse, sir, where we have to take moment. Moment at all the point, at any point you can take, because for entire system moment value has to be 0. So whichever point, if you want to take, like any point, if I have to take moment here or here or here, anywhere I can take, because I need to ensure the moment equilibrium across the system. It should not be like only at this point moment should be equilibrium, at this point some moment value is there. That should not be there. Moment equilibrium means across the system moment value is 0. The net moment value will be 0. So this is the basic understanding you should be having for static balancing, dynamic balancing. Now apart from that, what is required? Only simple equilibrium equations. If you have completely understand the engineering mechanics basic concepts of equilibrium topic. The very first topic in engineering mechanics is what? Equilibrium. That equilibrium topic only we need to apply here. Just we need to understand whether this is a case of a static balancing in a given question, it is a case of static balancing or dynamic balancing. Only that much difference I need to understand. If it is clear, then I will apply the respective equations of equilibrium and I will get whatever unknown they are asking. That's all in rotating masses. Clear? I hope this is clear to everyone. Yes or no? Just tell me. Any doubt, please ask in the chat box immediately at that moment only. Okay. Now one example I will give you here regarding the rotation on the same plane. Okay. Static balancing case, let's suppose we are discussing. Okay, now see here. right? So let's suppose this is the case we are having. This is the shaft, let's suppose. This is the shaft we are having, and let's suppose in this case we have three unbalanced masses like this. These are the three unbalanced masses we have. M1, M2 and M3. These are the three unbalanced masses. Now obviously it is a case of a same plane, masses are in same plane. The balancing mass required in this case will be only one. Only one balancing mass is sufficient in this case to balance this entire system. Now the main question here is, what will be the balancing mass required, what is the radial location of balancing mass required, and also what is the angular position of the balancing mass. All those details they will be asking, right? So first of all, let us assume somewhere the balancing mass is there. Let us assume any direction here. Let us take this one as the balancing mass. This is as balancing mass MB, right? And the radial location of M1 will be R1, simple. This is R2, this is R3, and here the balancing mass location will be RB, like this. Are you getting my point? So this is the system we are having. Now, very important point. Okay, what I will do here, because for this unbalanced mass M1 there will be Mr omega square, okay, and for M2 Mr omega square, M2 R2 omega square, M3 R3 omega square. These are the forces, and for this balancing mass MB RB omega square. So summation of all the forces should be 0 along x and y directions, right? Now very important point here. So let us draw this diagram in the front case, because we are observing from the side, that's why I have drawn like this. But while solving question, what I will do here, simply I will draw this in a rectangular coordinate system. Okay, now see. So the radial location that you will be having, the radial location of M1, radial location of M2 and radial location of 3, like this. So what we will be doing here, very important point, everyone should understand, all the radial location, angular position basically will be taking from the positive x. Let's suppose this is the positive x we are having. So from here, okay, please try to understand. This is theta 3, this is theta 2, and this is what we have as theta 1, like this. Angular positions, always from positive x will be taking in anti-clockwise sense. In anti-clockwise sense we will be taking, right? Now M1, M2, M3. Now regarding this balancing mass, somewhere here the balancing mass I have assumed, okay. For this, what is the angle required? Theta B. Theta B, right? And respective radial locations like R1, R2, R3 and RB I have mentioned here itself. Now the first step is what? Summation of forces along x direction 0. So you will be taking the summation of the horizontal component of all the forces. How you will be taking? See, M1 R1 omega square cos theta 1, like this. M2 R2 omega square cos theta 2 plus M3 R3 omega square cos theta 3 plus MB balancing mass RB omega square cos theta B equals to 0. Like this you will be writing. Now in a simplified form, how I will be writing, because actually I want this MB RB na, so I will take it one side, MB RB omega square will get cancelled out, so no need to write. It is become cos theta B equals to equals to minus, sign will be coming because all of these factors will be going on the right side. So minus mr cos theta, mr cos theta, like this. Clear? Right. So like this we will be having equation. In a similar way we can write it for the vertical direction as well. Okay, we can write it for vertical direction as well. So let me write it for vertical direction as well. For summation of forces in vertical direction 0. So directly I am writing MBRB sin theta B equals to minus summation MR sin theta. So this is your equation 1, this is your equation 2. This direct equation you should remember always. Okay, directly you should remember these two equations. Now what I will do, if I square and add both the equations, if I do the squaring and adding of both the equations, what I will be getting? See everyone. Equation 1, okay, directly I will write first square and second square if I do. So what I will be getting? MBRB whole square. Why? Because see, here the squaring if you do, cos square theta, sin square theta b. So sin square theta b plus cos square theta b will become 1. So MBRB whole square will be there. That's what I am writing here. And remaining two terms will be like this. MR cos theta square plus minus MR sin theta square whole square. From here you will get the answer directly. So what will happen in the questions of balancing of rotating masses? Either they will be giving balancing mass and they will ask radial location, or either the radial location will be given and they will be asking balancing mass. So from this relation you will get the answer very easily. Right, like this you will be getting. Now very important point here guys, when we have taken the components along x and y, okay, we can get very important point. See, we have taken horizontal and vertical components for all the forces. We get this equation 1 and equation 2. If I divide equation 1 and 2, if I divide equation 1 and 2, or basically 2 and 1, because sin theta divided by cos theta becomes tan theta, MBRB will get cancelled out. So this relation will help you to get balancing mass or radial location. If I divide equation 1, equation 2 and 1, first I have square and then add it, so we'll get this relation. If I divide equation 2 with equation 1, so you will be getting tan theta b. Okay, sin theta b divided by cos theta b, tan theta b. So you will be having minus MR sin theta minus MR cos theta. Now you will be wondering like why the minus sign I have kept. Minus sign can be cancelled out. No, please don't cancel out the negative sign, because this negative sign will be there when you will open this numerator and denominator. This minus sign has to be what utilized. Otherwise if you cancel out you will not get the actual answer. So don't cancel the negative sign. Very very important part. Don't cancel the negative signs here. So better I will write down here also. Don't cancel negative sign. Right, so this point you should remember. So from here you will get the location of theta b. So now all the parameters has been covered here. Balancing mass, okay, second radial location of balancing mass, and third the angular position also we have covered here. Right, I hope it is clear. Now going to the next part here guys, balancing of reciprocating masses. Now in the balancing of reciprocating masses, first of all we need to understand what is the unbalanced force here. Okay, so I hope you remember what is the acceleration that the slider will be having. Okay, because this is the basic thing, you should be knowing that part here. So there is what the unbalanced force will be acting here. That unbalanced force is nothing but mass into acceleration. Acceleration will be r omega square. Okay, r omega square in bracket cos theta plus cos 2 theta divided by n, like this. Now if I further open up the bracket here, what you will see, mr omega square cos theta plus mr omega square cos 2 theta divided by n, like this. Now very important point here, this is the primary unbalanced force, this is the secondary unbalanced force. This is very important information. This is primary unbalanced force and this is what the secondary unbalanced force. So now actually in reciprocating masses we cannot completely balance the unbalanced forces. In reciprocating masses it is not possible to completely balance the unbalanced forces in case of reciprocating mass. Because of that we will be doing the partial balancing. Okay, and remember we will take the unbalanced force as primary only. Secondary, for secondary we will not do the balancing. For secondary also we will be doing, but major part of the unbalanced force is because of this primary. Okay, if you compare the magnitude also, primary has more magnitude compared to secondary. So it is advised that first you need to try to balance the primary unbalanced force, then come up to the secondary unbalanced force. So here first of all some basics you should know. Primary is mr omega square cos theta and secondary is mr omega square cos 2 theta by n. Okay, I hope you remember n is the ratio of connecting rod divided by the crank radius. Length of the connecting rod divided by crank radius. This is there. Now, if I just compare the maximum value of primary unbalanced force, please try to understand. Sometimes they will be asking such a simple question also. The maximum value of primary unbalanced force is mr omega square and secondary unbalanced force maximum value is mr omega square divided by n, right, like this. So the maximum value of primary unbalanced force is mr omega square and maximum value of secondary unbalanced force is mr omega square divided by n. These are the two values that you should remember here. Correct? This much basics at least you should know. Now if you see the previous year question, you will not find that much numerical from this reciprocating masses. Still at least some of the basics you should be knowing. Okay, at least some of the basics part. Okay, because if the question they are asking in the GATE examination, you should be able to solve if they are asking such type of simple questions also. Okay, because see, even if we don't remember this basics, so then how you will be able to solve? So better just remember some of the basics part, right? Done everyone? Okay. Now very important part, please understand. For balancing, what we will do here, we will provide a balancing mass here. Okay, we will provide a balancing mass. So let me just draw the diagram for you here first of all. Okay, now see. So this is the slider we are having, and let's suppose this is the connecting rod, this is the crank, like this. Okay, now very important point. This theta is the crank rotation. Okay. Now this is what the line of stroke. Line of stroke basically means the direction along which the your slider or the piston will be moving. Now for balancing of this reciprocating masses, what we are going to do, we will provide a balancing mass here. Okay, balancing mass we will provide like this. Now this balancing mass will be provided. This is the radial location of balancing mass. Now what will happen because of that, its component will be like this and another component will be like this. Again this is theta. So this one will be MB RB omega square cos theta. This is MB RB omega square sin theta, like this. and here the unbalanced force was mr omega square cos theta, like this. This is the primary unbalanced force. We are doing the balancing of primary unbalanced force. I hope you are getting the point. So remember this point, mr omega square cos theta. Now what kind of question they can expect? The question they will be asking, what is the net force acting along the line of stroke? What is the net force acting perpendicular to the line of stroke? As I told you already, complete balancing is not possible. So we will do what? Partial balancing. And because of partial balancing, you will see some net force along the line of stroke. Net force along perpendicular to the direction of line of stroke because of the partial balancing. Complete balancing is not at all possible here in this case. Okay, so already in the classes, live classes, we have discussed so much things regarding why it is not possible here. So many details we have discussed in the class, but at this point of time we will be discussing only few important details here. Now, so what is the partial balancing here? See, for partial balancing part, okay, I will just mention here itself. Okay, for partial balancing, okay, for partial balancing, see, your MB RB will be equals to C times of M into R. This is very important point. MB RB equals to C times of M into R. C is what the percentage of balancing you have provided, like 60%, 70%. So your C value will vary between from 0 to 1. From 0 to 1. If the C value is 1, it means complete balancing you want to do it. But which is not possible, na? Complete balancing is not possible. So from 0 to 1 it is the value. So we will be providing either 100%, either 70%, 80%, 60% based on the question. We will be providing the partial balancing. So MBRB equals to CMR. This is the point we should remember. 60% balancing they have mentioned, so C value is 0.6. That's what you need to understand. I hope you are getting the point. Now, next thing, very important part. So what is the net force along the line of stroke? What is the net force along the line of stroke? So we will write it here. Along line of stroke. So it will be mr omega square cos theta minus mbrb omega square cos theta. So you can simply understand na, mr omega square minus mbrb omega square cos theta. Now mbrb can be written as CMR. Okay. mbrb can be written as C into M into R. Everything will remain same as it is. So finally 1 minus C, we will take common here, mr omega square cos theta then finally. This is what the final formula. Okay, so directly this formula you should remember, C is the percentage of the balancing you have provided, 60%, 70%. Now next is what the net force perpendicular to line of stroke. So the only force perpendicular to line of stroke is MBRB omega square. Into sin theta. So instead of MBRB, you can write C into M into R. Okay, so don't be confused if they have not provided the balancing mass. Okay, in reciprocating masses, if they have not provided the balancing mass, don't be confused. Okay. Because C is the fractor, we have to use it. C is the fraction, we have to use it, right? So, because some of the time, if you remember this formula only, and you don't know the conversion of MBRB into CMR, then you will be worried about MB value, which is not even in the question. They will provide the value of C. So, from the value of C, you can get the answer. Perpendicular to line of stroke also, along the line of stroke. The resultant answer will be square of this value, and take the square root finally. Under the square root, square of this value and this square value will be there, and you will get the resultant answer. Now most common question usually in the engineering services they have also asked, not in GATE they have asked till now, what is the hammer blow? Hammer blow is the vertical, maximum value of the vertical force. Vertical force to what? This line of stroke. This is what the line of stroke we are having. So the maximum value of the unbalanced force perpendicular to the line of stroke is called as hammer blow. So its maximum value is what? MBRB omega square. Its maximum value is MBRB omega square, right? So that becomes your hammer blow. I hope this point is clear, everyone. Done? Okay. Next, we will be discussing here the gyroscope part, right? Any doubts till now, everyone? Tell me. Okay, clear? Now see, in the gyroscope part, first of all, the basic part that you need to understand is what the rotation, how you will identify the rotation in terms of vector. See, in simple sense, we will tell, okay, clockwise rotation, anti-clockwise rotation. But if I have to represent rotation in terms of vector, I will be using right hand thumb rule. Okay, so basically, in the direction of rotation, I will curl my fingers, and the direction of thumb will tell us the direction of rotation in vector. Okay, now let us suppose this is what we have, x direction, this is y, and this is z. So let us suppose we have a disk here. Okay, now from the right hand side, okay, from this side, if you are observing, from the right hand side you are observing, and you have seen it is rotating anti-clockwise. It is rotating anti-clockwise. Okay, it is rotating anti-clockwise. So you will curl your fingers in the anti-clockwise sense, and the thumb direction will give you the direction of rotation. Okay, so the thumb is towards right, so we will draw the rotation vector like this. This is what the representation of rotation. This is the representation of rotation of this disk, which is rotating anti-clockwise from the right hand side. Accordingly, I will curl my fingers and the thumb will show the direction of rotation. Okay, so using right hand thumb rule, we can identify the direction of rotation. Okay, for representing the rotation in terms of vector, we will use right hand thumb rule. We will use right hand thumb rule. Clear? Now, correct. So this is what the basic representation. Now, if it is clear, then what we need to do in the gyroscope, what kind of questions they will be asking? Aeroplane cases and the ship cases. These are the two most common cases from which they will ask the question. Right, now I hope this diagram is clear here. Okay, so let's suppose what happened in the gyroscope. What happens actually? First of all, gyroscopic couple value I will directly tell you here. It is I into omega s into omega p. I is the mass moment of inertia value, which can be calculated using m into k square. K is the radius of gyration. Okay, k is the radius of gyration. Omega s is what? A rotation of your particular disk or whatever the thing you have, or shaft. Omega s. But omega p, precision velocity. What is that precision velocity? Okay, please try to understand. Let's suppose there is a shaft here in the horizontal plane. This is the shaft in the horizontal plane, and it is rotating anti-clockwise from right hand side. In the previous case I have told you, no? Anti-clockwise from the right hand side. So it is also rotating anti-clockwise from right hand side. So its rotation vector will be drawn like this. Now that shaft has taken a turn like this. Okay, try to understand. This shaft which is rotating anti-clockwise from the right hand side. This shaft is rotating anti-clockwise from the right hand side. So rotation vector will be drawn like this. Fine. Now this shaft is taking a turn in the left direction. This shaft is taking rotation. Okay, it is rotating in left direction. So there are two kind of rotations involved here. First of all, it is rotating about its own axis like this. It is rotating about its own axis, but apart from that rotation, it is also turning towards left. So when it will turn towards left like this, what will happen? Okay, how that rotation is possible? Because of active gyroscopic couple. Because of active gyroscopic couple, it is possible. So we will have this AGC, I will call it AGC, active gyroscopic couple, and opposite to that we will have RGC, which is reactive gyroscopic couple. So this shaft was rotating anti-clockwise from the right hand side. Fine. For that rotation vector I have drawn this one. Now this shaft is taking a turn. This is a separate motion provided to the shaft. It is taking a left turn. So how that particular motion has been provided? With the help of AGC, active gyroscopic couple. As a reaction to that, RGC will be acting on the shaft, reactive gyroscopic couple. Now usually we need to understand what is the effect of that RGC. What is the effect of that RGC? Now for the effect of RGC, again we need to use right hand thumb rule. Okay. For understanding the effect of RGC. For understanding the effect of RGC, we will use right hand thumb rule. Right hand thumb rule we will be using. Clear everyone? So how we will use right hand thumb rule for RGC? See, this kind of motion is happening in a horizontal plane. So that's why, remember, this is a horizontal plane. In horizontal plane it is happening. In horizontal plane the RGC is applying. So I will keep my right hand thumb in the horizontal plane. So the direction of arrow, this direction of arrow I will put my thumb in the direction of this arrow. So I will keep my thumb like this, and these fingers are rotating in anti-clockwise from the front. Fingers are curled in the anti-clockwise from the front, right? So these fingers are rotating in anti-clockwise from front. It means what? So anti-clockwise couple is acting on the shaft. Anti-clockwise couple is acting on the shaft. So what I will do here, okay, so effect of RGC. Now you can understand very easily the effect of RGC. So arrow, in the arrow we will keep my thumb, and the fingers, how the fingers are curled, it will tell us the couple direction, anti-clockwise from the front, like this. This is the couple. This kind of couple is acting on the shaft. Now because of this couple, what will happen? Okay, how this couple will be formed? See, there is force acting like this. There will be the force acting like this. So better I will draw it in the separate diagram here, then you can easily understand. So any general case I am taking here, okay. Now for this I have understood, because arrow is like this. So in the arrow I have kept my thumb, and the fingers rotation will tell us the couple direction, anti-clockwise from front, anti-clockwise. So which means this kind of forces. Now this kind of forces acting on the shaft. So what will happen? This end will try to move upside, and this end will try to move in the downside. That is what the effect of gyroscopic couple. I hope you got this point. The right side will go in the upward and the left side will go in the down. That is what the effect of gyroscopic couple. Right, so this basics at least we need to know. Then only we can understand the case of aeroplane, and we can also understand the case of ships very easily. Now moving to the case of aeroplane first of all. Now what is given in this particular case? The propeller shaft is rotating in anti-clockwise direction when viewed from the RHS, right hand side, and it takes the left turn. Now we need to tell what is going to happen, okay. We need to tell what is going to happen on the aeroplane because of that reactive gyroscopic couple value, okay. Now see. So let us draw some diagram of aeroplane here. Okay. Like this. Okay, some aeroplane I have drawn here. So here it will have some propeller shaft like this. Now they are telling it is rotating anti-clockwise from the right hand side. So I will curl my fingers in the anti-clockwise sense and thumb will give me the direction of rotation. So direction of rotation is like this. Okay, fine. Now it is taking a left turn. If it is taking left turn, it will move like this. Now remember, it is all happening in a horizontal plane. It is all happening in a horizontal plane. So for that, what is involved here? AGC. Okay, and opposite to that, we will be having RGC, reactive gyroscopic couple. Now, if I see the RGC, the thumb will be in the direction of arrow. So as it is happening in a horizontal plane, thumb will be like this. Fingers will be curled like this, anti-clockwise sense. So what will happen? What will happen to your propeller shaft? Anti-clockwise couple will be acting, and because of this anti-clockwise couple, I can say this side will go up and this side will go down. Then only the anti-clockwise couple will form, na? So basically, we will say this nose part goes up and tail part, or the rear side, tail part goes down. Nose part goes up and the tail part goes down. That is what the effect of RGC on the aeroplane. I hope this point is clear to everyone, right? So this is what the basics, at least you need to know. Okay. Now the next thing that we need to discuss here is the ships. But in the ships, there are some terminologies that we need to discuss. Okay. That what is the terminologies? So let's suppose this is the front view of the ship here. So the right side will be known as bow, or the left side will be called as the stern. So these terms we should remember. Front, right side bow, left side stern. And if I observe the ship from the top, the left side turn if I take, I will say moving towards port, or if it is towards right, I will call it starboard. Or basically when I take left or right, we will say steering towards starboard, steering towards port. This kind of terms we will be using. So at least we should have this image in our mind before solving the ship's question. Correct, everyone? So this diagram is very important. Please make a note of this diagram first of all. Okay, then only we can discuss further. Just make a note of all these points, everyone, first. So let's suppose the first case we will be taking steering. So ship steers towards left, let's suppose. What will happen if the ship steers towards left? So steering towards left. So this motion is happening in horizontal plane. First of all, understand the plane of rotation. So if I talk about the steering, okay, this is happening in a horizontal plane. Right, like this. Now steering, so this is the propeller shaft. Let's suppose I am assuming anti-clockwise from the right hand side. So this is what the propeller shaft will be there. Rotation vector of propeller shaft. It is having a steering towards left. So this will be the rotation. For that there will be a AGC, active gyroscopic couple, and opposite to that there will be RGC. Now effect of RGC on the propeller shaft, again thumb towards like this and the fingers will be curled like this. It means what? Anti-clockwise couple on the propeller shaft. So anti-clockwise couple on the propeller shaft basically means in this case, what does that mean? So as I told you, you should remember this point. Bow part will go in the upside. Bow part. And the stern part will go down. That is what we need to conclude from this analysis. Clear? Right, now coming to the pitching part. Okay, coming to the pitching part. Now what is pitching here? It is the angular motion about the transverse axis. angular motion about the transverse axis. Pitching will happen like this. And this pitching is happening in which plane? Steering will happen left or right in a horizontal plane. Ships will move left or right, it is happening in a horizontal plane. But when pitching is happening, it is in a vertical plane. So plane of rotation you should also be clear. Without knowing the plane of rotation, you cannot understand the rotation. Plane of rotation is very important. So in pitching case, as I told you, it is the motion, angular motion that is happening about the transverse axis. Okay. So for steering, either it will be moving towards left or right. Pitching, it will move like this. So now in, let's suppose pitching up case I am taking, pitching up, for example, pitching up. So it will have like this, pitching up. So again, see, you will have this active gyroscopic couple, reactive gyroscopic couple. Okay. Again, I have drawn the rotation vector by assuming, remember the point, I have assumed the rotation vector that it is in the what? It is rotating anti-clockwise from right hand side, so rotation vector will be like this, towards right. So this is RGC. Now what will happen because of this RGC? Thumb I will show in, now it is happening in vertical plane, thumb in the downward direction. How the fingers are curled? Clockwise from the top. From the top, if I am observing, it is rotating clockwise. So from the top it is rotating clockwise. So where the ship will move? Towards right side, and towards right side we have what? Starboard. So because of pitching up, okay, for pitching up case, what will happen? Ship will steer towards starboard. Because RGC like this, clockwise from the top. Clockwise from the top means it is moving towards right. Moving towards right basically means starboard. That is what the effect of RGC whenever it is a pitching up case. Done? Clear? So that's how we will figure out what is happening, what are the effects of RGC. So please try to remember this case. Without knowing these terminologies, you can't solve the ship problem. Okay, again, gyroscopic couple formula is same, I omega s into omega p. Now the third part, everyone try to understand. Third part is like a rolling of the ships. In the rolling case, what is the effect of reactive gyroscopic couple? Okay, first of all, what is the reactive, this gyroscopic couple value if it is a rolling case? See, first of all, gyroscopic couple is happening because of the change in the direction of rotation. Change in the direction of rotation basically. And if the rolling motion means the rotation provided along the longitudinal axis. So both the vectors are along the same direction, so there will not be any change. So there is no change means what? There is no acceleration, no gyroscopic couple will be there. Okay, there will be no gyroscopic couple, right? So this is what you need to understand in the case of rolling. No gyroscopic couple will be there in case of rolling. Okay, so right, this is what very important part. Now next, the last thing that we need to discuss here is vibration. Very, very important thing. Entire theory of machine, vibration is very important. So I will summarize all of the formulas that you need to remember before the gate examination. At least you need to revise those formulas that I am mentioning here in this particular session. Okay, so one by one we will discuss all the formulas here. Okay, so first of all, this spring mass case. Stiffness K. So first of all, the natural frequency omega n under root K by M, unit is radian per second. Remember, K should be in Newton per meter, very important point. Now, if I have to calculate frequency in hertz, so omega n by 2 pi. Time period 1 by frequency, you will get the second. So this basic three formulas at least you should remember. Okay, regarding this spring mass case. Apart from that, series combination, if I talk about series combination, this is K1, this is K2. So how you will write equivalent stiffness? Equivalent stiffness will be calculated by using this relation 1 by K1 plus 1 by K2. This basic relation you should know. For parallel, what we will do? We will just add. Okay. Okay, so your equivalent stiffness in case of parallel will be K1 plus K2. This is the formula we should remember here. Now, these two things. Now, next is what the different kind of vibration that we are having. Longitudinal vibration, transverse vibration, torsional vibration. These are the three standard format of vibrations that we can have. So, first of all, longitudinal vibration. Okay, now see, first of all, in longitudinal vibration, what happens here? This is some rod, this is some element, and this is what some mass we have kept. For this case, static deflection will be P into L divided by AE. P is basically this load. So how to get the natural frequency for this kind of vibration? Simply G by delta. You will get the answer. So this was longitudinal vibration. Now next is transverse vibration. In transverse vibration, let's suppose we have a cantilever beam. In cantilever beam, you have kept some mass at the end. Okay, some mass you have kept here. So obviously, if you have kept some mass here, point mass at the free end, you will have some deflection. Static deflection you will be having. So that static deflection formula you will get it from the strength of material, WL cube by 3EI for this case. So again, natural frequency you will calculate using G by delta, radian per second. Clear everyone? So this longitudinal vibration, transverse vibration, these two are very important here. Now one more thing, torsional vibration here. So here itself I will write. In torsional vibration, what happens? Let's suppose this is the element here, and what happens here? Some disc has been attached. Okay. So some angular disturbance theta you have provided here, like this angular disturbance you have provided, and because of that it will vibrate, starts vibrating. For that case, you should remember the natural frequency will be under root KT by I. What is KT? Torsional stiffness, which is torque divided by theta, or can be written as GJ by L. In this case of transverse vibration, bending stiffness, okay, bending stiffness will be EI divided by L. EI can also be called as flexural rigidity. Remember this point. Product of EI is also known as flexural rigidity. And actually this was the question asked previously. Flexural rigidity. This thing you should remember. Okay. Now this basics we have covered. Now very important part, if the damper is what installed here. Okay, damper is what installed in the spring mass system. We have not used damper. Now damper will be included. After that, force will also be get included here. So just we'll write here first of all the basic part here. Types of systems we can have. First of all, we will have undamped. So damping factor value 0. Here damped system. So we will have three cases here: over damped, critically damped, and third one under damped. Right, it is under damped. Now one more thing you should remember, over damped means damping factor greater than 1, here damping factor equals to 1, and here damping factor less than 1. This is what the characteristics of the system. If the damping is provided, either it can be over damped, critically damped, or under damped. This is very important, how to understand what kind of system they have provided. So if it is undamped, damping factor is 0. Okay. Now what is damping factor? It is the ratio of damping coefficient divided by critical damping coefficient. So you can write it like this, 2 into under root k into m, which can also be written as c divided by 2m into omega n. So this formula you should remember. Clear everyone? So now undamped system case we will be discussing here. Okay, for undamped system case, and then after that logarithmic decrement, very important part. Okay, for undamped. Okay, for undamped system, your displacement will be x, capital X becomes what? Your amplitude. It is equals to damping factor omega n Td. Right, this is what the formula that we will be having. Okay, it is Td, Td will come here, sine, okay, Td, omega n Td plus phi, like this. This is what the solution that we will have. Okay, complete derivation is involved here, but I am directly writing the solution part because this is what we need to understand at what kind of conclusions we can draw from it. So this is the solution of underdamped system. Underdamped system we will be writing. It is underdamped, not undamped. Let me just write it here, underdamped. Underdamped, which means damping factor is less than 1. Now, very important part, this amplitude, better write it like this, amplitude decreases with time. But how it is decreasing? Exponentially it is decreasing. Amplitude is decreasing with time, right? Correct, but exponentially it is decreasing. So this is very important part. Exponential decrement of the amplitude in the case of underdamped system. So if I put t equals to infinity, amplitude of vibration will become 0. Right? So simply because e to the power minus t is there now, so if I put t as infinite time, then amplitude of vibration will become 0. But practical case we will talk about, as the time increasing, amplitude of vibration is also decreasing. That is what the practical understanding we can have from this particular solution. So all these solutions has been done, okay, for the given system. Complete derivation has been done, and then finally this result will come. So we will be discussing this final result here. Okay. Now in this part, one more thing you need to understand here, the logarithmic decrement part, very important. Now questions will be coming from directly from logarithmic decrement. Now what is logarithmic decrement? Logarithmic decrement is actually the natural log of two successive amplitudes. So it is represented by this factor del, natural log of two successive amplitudes. Okay, and its formula can also be written as like this, 2 pi into damping factor divided by under root 1 minus damping factor square, like this. Got it? So these two formulas at least you should remember. The direct two formulas, either sometimes this one is useful or sometimes this is useful. Okay, both the formulas are very important for logarithmic decrement. Done everyone? Done? So as I told you, in the case of underdamped system, the ratio of successive amplitudes is constant here. For example, if I am writing x0 by x1 equals to x1 by x2, x2 by x3, and so on, like this. Ratio of successive amplitudes. ratio of successive amplitudes is what? Constant we are having, and that constant value equals to e to the power del. Del is what? Logarithmic decrement. Now what happens here in the question, they will give from 5th cycle to 8th cycle, the ratio of 5th cycle to 8th cycle, like x5 by x8 they were telling. So I can calculate what actually x5 by x8 is. Okay, like x0 by x1, x1 by x2, x2 by x3, like x3 by x4, all are equal and all are having a value e to the power del, right? So this is very important point, guys. I'm telling you, this relation, this is also very important. Apart from these two formula, this relation is also very important, so you should remember that formula as well. Done? Okay, now next that we will be discussing is the forced vibration, single degree of freedom and forced vibration. Okay, now see, so some kind of force it is acting here, F naught sine omega t, like this. Let's suppose stiffness K, damping coefficient C, right? So how you will be writing equation here? Mx double dot plus Cx dot plus Kx equals to this F naught sine omega t. Instead of sine omega t, it can also have a cos omega t also. Okay, that is not a point here, because some kind of variable force is acting here. So it can be in terms of sine, it can be in terms of cos as well. So there is not a problem for that. Okay, so we can take it as per the given situation. Now in this case, what we need to remember here, very important part, amplitude of steady state vibration. There is a very important term here, amplitude, from which directly so many questions they have asked. Okay, directly so many questions they have asked, amplitude of steady state vibration. So that amplitude of steady state vibration is basically F naught divided by K divided by under root 1 minus R square whole square plus 2 into damping factor into R whole square. Now what is R? R is the ratio of frequency omega by omega n. What is omega? Omega is our excitation frequency, omega n is the natural frequency, right? So this point you should remember. And this is what the damping factor, F naught is that force and K is the stiffness of the spring. So amplitude of steady state vibration basically means that vibration amplitude is not going to change forever, no matter whatever the time is. No matter whatever the time is, that amplitude of steady state vibration is not going to change. That's why it is mentioned steady state, independent of time. I hope you are getting this point. Okay, so this is there. Now next thing that we need to remember here is the magnification factor. So that magnification factor, okay, how you will be writing magnification factor? See, the formula I will tell you here, it is 1 by under root 1 minus R square whole square plus 2 damping factor into R whole square. This is what the magnification factor we are having. Okay, so amplitude, it is the ratio of amplitude of steady state vibration divided by static deflection. This is equals to amplitude of steady state vibration divided by F naught by K, static deflection, like this. Now this relation is also very important here. Okay, now there are some cases that you should remember here. Okay, there are some cases that you should remember. So for example, case number 1, if R value equals to 1 and damping factor is 0. R value 1 means omega, excitation frequency equals to omega n, which means what? The resonance condition, right? And 0, damping factor 0 means undamped system. So what will happen? Magnification factor will become infinite. Magnification factor become infinite. Okay. Now case number 2. if R value is 1 and damping factor is having some value which is constant, then what is the value of magnification factor? R value 1, so this becomes 0, R value 1 here. So magnification factor is 1 by 2 into damping factor, 1 divided by 2 into damping factor. Very important point. If someone says, if resonance condition is there, so magnification factor is infinite, yes, true, if no damping is provided. But if damping is provided, it is not infinite. Remember this point, always, very, very important point, everyone. This is very important point. Okay. So this magnification is very important part, magnification factor, right? Now after that, what you need to remember, the transmissibility factor. Transmissibility ratio basically. Okay, so this transmissibility ratio, the formula, under root 1 minus divided by under root 1 minus R square. Like this. Now actually this ratio is representing what? Ft divided by F naught. So force transmitted to the ground divided by the force applied. Transmissibility ratio is actually the measure of the performance of vibration isolation system. So from this ratio, what we are actually checking? We are checking the performance of the vibration isolation system. So it is the ratio of force transmitted to the ground divided by the force applied to the ground. So that's why this ratio is very, very important, everyone. So you should remember, maximum time numericals have been asked from this one. So you should not miss this part. And one special thing that you should remember here, the condition. This case you should remember, case 1, let's suppose. If R value is less than root 2, if R value is less than root 2, then transmissibility is greater than 1, which means force transmitted to the ground is more compared to the force applied. And if R value is greater than root 2, then transmissibility ratio is less than 1. Transmissibility ratio is less than 1, that is force transmitted is less than compared to F naught. Clear? So this is what very important. So this case 1 and case 2 you should directly remember. Okay. So that is what the last topic, that at least this much part you should know. So whatever formulas that we have discussed in the vibration, you can expect some numerical from it. Right? And please revise your subject, do maximum revision, don't try anything new, okay, at this moment, because only few days are left for your GATE examination. So all the best from IMS GATE Academy team. Okay, and whatever challenges you are having during the preparation part, guys, we are always with you, entire IMS GATE Academy team with you. And be confident, keep doing the practice of the previous year question at this moment, don't try anything extra, right? And all the best from our entire IMS GATE Academy team. Thank you so much, guys. Bye-bye.